Hello all, have a nice time. In the last class, we have discussed the concept of orthogonal projection of a vector on another vector. Today, our topic of discussion is orthonormal basis. We have already studied about vector spaces and the basis of a vector space. Today, we will study to construct a basis consisting of orthonormal vectors. Then such a basis is called orthonormal basis. So first, we will These are the answers to the problems assigned in the last class. So first of all, let us check what you meant by orthogonal set of vectors and orthonormal set of vectors. A set S of vectors in an inner product space V is called orthogonal if every pair of distinct vectors in S is orthogonal. We have already studied about how to check two vectors are orthogonal. If U and V are two vectors, if U dot V equal to 0, then we say that these two vectors are orthogonal. In R2, for example, let us take the vectors 1, 0 and 0, 3. Okay. So first vector U lies in the x-axis and the second vector V lies in the y-axis. And these two vectors are actually perpendicular vectors. And when you take the dot product, it gives 0. 1 into 0 plus 0 into 3, it gives 0. So we say that these two vectors are orthogonal. And if you have a set S, and if every pair of vectors in S is orthogonal, then we say that this set S is an orthogonal set of vectors. Okay. And if in addition, every vector in S is a unit vector, then S is called orthonormal set of vectors. And here, if we consider the set 1, 0 and 0, 3, this is an orthogonal set of vectors. The set is S. This is orthogonal set of vectors because these two vectors are orthogonal. And if I take the vectors as 1, 0 and 0, 1, it is orthonormal set of vectors because these two vectors 1, 0 and 0, 1 are orthogonal and also each of one is a unit vector. So we can conclude that this set S dash is an orthonormal set of vectors and S is a set of orthogonal set of vectors. For another example, in R3, you may consider the vectors U equal to 1, 0, 0, V equal to 0, 1, 0, and W equal to 0, 0, 1. We have already known that this set UVW is a standard basis of R3. Okay. Now you can check that whether this set is we consider set UVW. We have to check whether this set is orthogonal. Okay. So how to check? We have to take every possible pair. So we want to check U dot V, then we have to check V dot W and also U dot W. So you know that U dot V is actually equal to 0 here, this also 0 and this equal to 0. So we check whether any pair of vectors, if we take any pair of vectors, the dot product is 0. Okay. So the set of vectors S equal to set U V W is an orthogonal set of vectors. Okay. And also we know that when you take the norm of U, the length of the vector U is square root of 1 square plus 0 square plus 0 square, that's equal to 1. And norm V also equal to 1 and norm W equal to 1. So this is an orthogonal set of vectors. Also, all the vectors U, V, W have unit length. Therefore, we can conclude that this S is an orthonormal set of vectors. Also, we know that this set is the standard base of R3 or it's the basis of R3. Okay. So as we see in the example, if an orthonormal set is a basis for a vector space, then it is called an orthonormal basis. So suppose you have a set S. How we will check that it is an orthonormal basis of a vector space? First of all, you have to ensure that it is a basis of the vector space. So what are the conditions for the basis of a vector space? The set must be linearly independent and it spans the vector space, V. Okay. Then S is a basis. In addition, if the set S is an orthonormal set, that is, if you take any two distinct vectors in S, U and V, U dot V equal to 0, and norm of each vector in S equal to 1. If S satisfies these two properties also, then we call this S as an orthonormal basis. Now let us go through some examples. Standard basis of Rn, that is 1, 0, 0, etc. 0, 0, 1, etc. 0, 0, 0, etc. 1 is an orthonormal basis of Rn. We know that it's a standard basis and also If you take any two distinct vectors in the set, it is orthogonal, that is dot product equal to 0. And we also know that norm of each vector equal to 1. So this is an orthonormal basis of Rn. As another problem, we have to show that this set is an orthonormal basis for R3. So first of all, we have to show that it is an orthonormal set. So for that, we will take each pair. Let us have this vectors as v1, v2 and v3. We will check whether v1 dot v2, v1 dot v3 and v2 dot v3 are all zeros. So what is v1 dot v2? It is 1 by root 2 into minus 2 by 6, that is minus 1 by 6. Then 1 by root 2 into root 2 by 6, that is 1 by 6. 0 into 2 root 2 by 3, that's equal to 0. So sum is equal to 0. So in the similar way, you can check whether v1 dot v3 equal to 0 and v2 dot v3 equal to 0. So if you take any two pairs in the set S, you can show that these two vectors are orthogonal. So the set is an orthogonal set of vectors. Next, we will check whether each vector is a unit vector by calculating its norm. So what is norm v1? v1 was the vector 1 by root 2, 1 by root 2, 0. When we take the norm, it is square root of 1 by root 2 square, that is 1 by 2, plus 1 by root 2 square, that is 1 by 2 plus 0, which gives 1. Similarly, you can see that norm v2 equal to 1 and norm v3 also equal to 1. So the set S consists of orthogonal and unit vectors. Therefore, S is an orthonormal set. So we proved that the set is orthonormal. Now to show that it is an orthonormal basis for R3, you have to check whether it is a basis of R3. So to show that S is a basis, we have to show that S is linearly independent, also S spans R3. Okay? So to show that it is linearly independent, you know the easy method. You will consider the vectors as columns of the determinant. So we have determinant 1 by root 2 minus 2 by 6, 2 by 3. So that's the first coordinates of the vectors. Then you have 1 by root 2 to root 2 by 6 minus 2 by 3, 0 to root 2 by 3, 1 by 3. You have already studied how to construct this determinant and what's the relevance of this determinant. So when you iterate the determinant, you can show that the determinant equal to 1, which is not equal to 0. So we have the result that if you have a system of linear equations Ax equal to 0 and if determinant of A not equal to 0, then this system has a unique solution. So using this result, we may conclude that the set S is linearly independent. We have already discussed these topics earlier. And how can we conclude that H spans R3? You have a result again. The set S is linearly independent as S contains three vectors here. And we already know the basis of R3 contains three vectors. So the set is linearly independent. Also, it spans R3. So we can conclude that S is a basis. So here S is a basis. We have already shown that it is orthonormal. So we can conclude that S is an orthonormal basis of R3. Actually, in the next theorem, we will prove that if you have an orthogonal set of vectors, it will become automatically linearly independent. So for this problem, actually, we do not need to check whether it is linearly independent. If you can show that a set is if the set is orthogonal, then it becomes automatically linearly independent. So let us go to the theorem. If S equal to set v1, v2, etc. vn is an orthogonal set of non-zero vectors in an inner product space V, then the set S is linearly independent. Before going to the importance of the theorem, let us have the proof of the theorem. Here we assume that S equal to set v1, v2, etc. vn is an orthogonal set of non-zero vectors. We have to show that the set is linearly independent. How can we show that a set is linearly independent? We will consider the linear equation C1 V1 plus C2 V2 plus etc. plus Cn Vn equal to 0, and we will show that all the coefficients C1, C2, etc. Cn are zeros. So the method is, we will take an arbitrary vector in S. S contains the vectors V1, V2, etc. Vn, and we are taking an arbitrary vector Vi. Then finally, we will show that the coefficient of Vi equal to 0. That means that Ci equal to 0. Since I varies from 1 to n, it concludes that all the Ci's are zeros. That is a method. So we are taking an arbitrary element Vi belong to us. Then we are considering a particular inner product. Inner product Vi comma C1 V1 plus C2 V2 plus etc. plus Cn Vn. This sum actually is a vector which belongs to the vector space V. So when we consider this inner product, by linearity property, we may write it as C1 into inner product Vi V1 plus C2 into inner product Vi V2 plus etc. plus Cn into inner product Vi Vn. And the ith term becomes Ci into inner product Vi Vi. So that term is written here. So what happens to the left hand side? Here the sum C1 V1 plus C2 V2 plus etc. plus Cn Vn is assumed to be 0. So we can substitute 0 here. And this inner product becomes inner product Vi 0, it becomes 0. And what happens to the right hand side? In the right hand side, the ith term is inner product Vi Vi. Here only the vectors Vi and Vi are equal, and in all other terms of the sum, Vi V1, these are distinct, Vi V2 are distinct, etc. Vi Vn are distinct. So all these in the product becomes 0 because we know that this set V1, V2, etc. Vn is an orthogonal set of vectors. So if I not equal to j, Vi and Vj are distinct and their dot product becomes 0. That means that corresponding inner product equal to 0. So in the right hand side, the only remaining term becomes Ci into inner product Vi Vi. And in right hand side again, this is Ci into norm Vi square. And this product equal to 0 means that either Ci equal to 0 or norm Vi square equal to 0. But we already assumed that set S contains non-zero vectors. So Vi is not equal to 0. Therefore norm Vi square is not equal to 0. So which implies that the Ci equal to 0. So Ci means it's a coefficient of Vi, and Vi is an arbitrary element in the set V1, V2, etc. Vn. This implies that all the Ci's are zeros, where I belongs to 1, 2, etc. n. So this proves that S is linearly independent. Hence, as per this theorem, if S is an orthogonal set of non-zero vectors in an inner product space V, then that set is linearly independent. So if you have an inner product space V, you know that it is a vector space and it has a basis. And how you could identify a basis using this property? If you could identify a set of vectors V1, V2, etc. Vn in V, which is non-zero and orthogonal, then automatically it becomes linearly independent. There is no need to check whether the set is linearly independent or not, as we have done in the last problem. So actually in the last problem, we had to check the set is an orthonormal basis for R3. So you need to check whether it is an orthonormal set. Since it is orthonormal, it is automatically orthogonal because an orthonormal set means that it is orthogonal and all the vectors are of unit length. So this is an orthogonal set. If it is an orthogonal set, automatically it is linearly independent by the theorem we have discussed. And since the basis of R3 contains 3 elements and this is a linearly independent set with 3 elements, it is a basis of R3. So we can conclude that this is an orthonormal basis of R3. So it is enough to check that the set is orthonormal or not. So using the theorem, let us have a problem again. Determine whether B equal to sin theta cos theta minus sin theta is an orthonormal basis for R2. So let us compute the dot product of the vectors sin theta cos theta and cos theta minus sin theta to show that it is orthogonal. So the dot product becomes sin theta cos theta plus minus cos theta sin theta. It becomes 0. So this set is an orthogonal set of vectors. Now we have to check whether it is of unit length. So what's the norm of the vector sin theta cos theta? It is square root of sin theta square plus cos theta square. It's equal to root 1. That's equal to 1. And for the second vector also, the norm is equal to 1. So we have shown that these two vectors are orthogonal and is of unit length. Therefore, the set B is orthonormal. And as per the theorem, since it's an orthogonal set, it is linearly independent. And we know that the basis of R2 contains only 2 elements. This set B also contains 2 elements. So we can conclude that it is a basis of R3. Sorry, basis of R2. Therefore, B is a basis for R2 and it is orthonormal also. Therefore, it is an orthonormal basis of R2. One more problem. Show that the set B equal to 2, 3, 2 minus 2, 3, 0, 0, 3, minus 1, 0, 2, 1, minus 1, 2, minus 1, 1 is a basis for R4. First, we will show that B is an orthogonal set of vectors. So you have to take pair of two distinct vectors from B. So the possibilities are u1 dot u2, u1 dot u3, u1 dot u4, u2 dot u3, u2 dot u4, and u3 dot u4. And you have to show that all these dot products are zeros. So this set B is an orthogonal set of vectors. And by the theorem, you can conclude that it is linearly independent. Since it is linearly independent and it contains 4 vectors and the basis of R4 already contains 4 vectors, therefore we can conclude that it spans R4 also, hence it is a basis for R4. So it is enough to check that whether the set is an orthogonal set of vectors to show that it is a basis for R4. These two problems are assigned to you for today. First problem is to show that the given set is an orthogonal set and you have to show that it is a basis for R4. And in the second problem, it is enough to show that given set is orthonormal.